I'm gonna list and prove some of the very important commutation relationship in the quantum mechanics that you should know, and they are general in the question form in the Griffith's quantum mechanics. That's why I've picked up from that, and we are gonna prove this, and they're quite easy. A one-star problem in the Griffith's quantum mechanics and the one-star problem are quite easy. So some of the general are, first is, I guess the first one is very easy. That suppose that there's a relationship, commutation relationship between a sum function f of x, and you get here with the momentum operator, and you want the commutation relationship. So if you evaluate this particular relationship, you will get as iota h bar the derivative of that particular function with respect to the x. So yes, this is what you're gonna find out when you will evaluate this. So let me write it clearly, that this is the commutator of the function with the momentum operator, and you will evaluate this. Okay, so you will get it iota h bar the derivative of that particular function. So this is what you will find out. So I'm going to quick proof of this particular result, which is quite easy. If you haven't done this, then it's okay, because these are something which you can do in a minutes or in a matter of seconds. And this is like, suppose that you choose a test function, and our test function is going to be, let's say, g of x. Suppose that you have a test function acting, and you have f of x and the momentum operator here, and we have a test function g of x. Okay, now we will evaluate this. So see, now there's a real game. So according to the commutation relationship, we evaluate this. You will get as momentum operator, then f of x first of all acting on g of x, then you got minus here f of x, 1 minute, here f of, okay, so here you have got f of x, then the momentum operator acting on this particular g of x. Okay, now here you have to keep eye on that this momentum operator will act on f of x, then g of x, like the product rule, and when you will evaluate this, you will get momentum operator, 1 minute, write it better fashion. Okay, first of all it will act on f of x, so g of x can put outside, then this momentum operator acts on the f of x, then plus this particular momentum operator acts on the now g of x, so we'll put f of x aside from this, then this momentum operator acts on the g of x, 1 minute, okay, this will now act on the g of x, and you have minus this, which I'm gonna write down here, which is the f of x, momentum operator, and g of x. So this is what you will get, and essentially if you see carefully, these two particular things cut out, and you are left with this particular result, g of x and p of x acting on f of x. Now essentially g of x was our test function, so we will drop out the test function and see what our commutation relationship is without that particular function, so which is essentially the f of x, momentum operator, and removing this particular test function, you will get this result, p, a momentum operator acting on that particular function. And if you will write the momentum operator in the formula or in the equation of that, then you will get it as the minus iota h bar df by dx. So this is what we have to prove. This is very important result, and yes, quite easy to prove. These types of things are not discussed in a separate manner because these are quite easy and any student can figure it out if they are doing any of the particular courses and the questions. That's why these are not generally discussed widely, but I am trying to discuss it because, you know, it's good to keep eye on these types of stuffs. So this is our first relationship. So we can define this, we can use this result to see what is the commutation relationship between the x to the power 1 minute. We can use this particular result to find the commutation relationship between the x to the power n and the momentum operator. And if you have seen the result, you can directly write it as iota h bar negative, and the derivative of function, and our here function is, so I'm gonna remind you that, let me put it as some sort of example of this. Okay, so here our f of x is this x to the power n. Okay, and I'm gonna differentiate it, and you know your differentiation is n x to the power n minus 1. So this is the result, and this is also a question in the Griffith's quantum mechanics, but the more general one to this is this particular result. Okay, if you remember this particular result, you can figure it out on your own that what will be this particular thing. Okay, this was our first result. Now moving toward the second result, which is also quite very important, and which is that, suppose that you have a and b, two operators, okay, which do not commute. So the commutator of a and b operator, let's say c, then the result is the a commutes with c, yes, and same goes for b. B also commutes with c, and this is very important thing you have to know, and I'm going to prove this. And with the help of an example, which is again a very famous relationship, which is the between the momentum and the position. So I'm going to prove this result using the example of the momentum and the position operator commutation relationship. How? So let's see here. We all know this particular very famous result, that the commutation relationship between the position and the momentum operator is equals to the iota h bar. So here our a operator is x, b operator is momentum operator, and c is iota h bar. And we are going to prove this, that first, when this particular commutation relationship between the momentum operator and iota h bar is equals to 0, we are going to prove this. And so let's start the proof. Okay, so how are we going to prove this? So always pick a test function. Let's say our test function is f of x, and I'm going to choose it. Okay, so always choose a function, and it is iota, 1 minute, okay, iota h bar. Okay, and our test function f of x, and we will evaluate this particular function. You will get first of all iota h bar here, because first of all x will act on this particular function, then iota h bar will act on this. So x bar, 1 minute, let me put iota h bar first outside of this relation. Okay, so first of all this iota h bar will be out from this particular result, iota h bar. X will act on this particular f of x. Okay, and then of course minus, then this particular iota h bar will be here acting on this particular function. Now this particular, okay, so this is a result, and if you see carefully here, that the formula of the x operator is just x, So if you see carefully, that this particular iota h bar x f of x is just similar, equal to our result x iota h bar f of x. There is the same, whatever the ordering is. Okay, this is the same. It means if these are equal, I can just cut it out. Yes, eventually you can do this, and if you will do this, you will get 0. And yes, we have proved that this a and c commute. Now the second thing is, for the momentum operator, is that the momentum operator and this particular iota h bar commutes with each other. This is also quite easy, but you should know this because it will help. These are like some of the small tricks that you should know, which will not harm you. Okay, so here you have iota, 1 minute, let me write it clearly. You have iota h bar, and we are going to prove this, that this commutation relationship is also equals to the 0. Now again we are going to choose a test function and we'll evaluate it. So choose a test function, let's say f of x, and evaluate it. First of all, the momentum operator acts on f of x, so this is essentially iota h bar out from this particular relationship, because first of all it will act on this. 1 minute. Okay, so it will, first of all, if we put out iota h bar out of this relationship, this momentum operator will act on f of x, then minus of iota h bar will act on this, so this is momentum operator, then iota h bar f of x. So this is the essentially our relationship. And if you see carefully here, that iota h bar p and f of x minus, since iota h bar is a constant, you can take it out from this particular you can say product rule, because suppose that you have some sort of differentiation of 2x, you always put out 2 from this relationship, from this action. Okay, so you can just put it out outside this iota h bar, and this momentum acts on function x, function of x only. Okay, and if you see it carefully that these two results are exactly similar, again you can cancel this out and this is equals to the 0. So yes, we have proved the result. We have proved a result that we have stated that if there are operators a and b that do not commute with each other and it is equals to c, then it should be that this is equals to 0. And again this case for the b commutation relationship with the c is 0, and we have proved this using the example of the momentum and the position operator. So these are some of the essentials relationship in the commutations in that you have to remember. One very important commutation relationship also is between the raising and the lowering operators in the quantum mechanics, which I'm giving you as some sort of like homework or things that you should do on your own. It will be quite lengthy but not easy. It will be quite lengthy but not hard. Okay, so you have to find the commutation relationship between the I guess the question number of Griffiths is I actually don't remember correctly, but you should find out. I guess I don't remember it correctly that what exactly was the question, but it was regarding some sort of ladder operators and Hamiltonian, I guess. Yeah, it was like that. Okay, so you can check that on the section of, I guess, chapter number 2 on the harmonic oscillator, and there is a question on that particular commutation relationship between, I guess, Hamiltonian and something which I don't remember, but yeah, it involves the ladder operators, and you should evaluate that also. It's a quite easy question but a lengthy one. You have to do a lot of manipulation stuffs and differentiations to do that, but again it's not that hard. These are like easy and you have to do that. One again important thing is that when you study the quantum mechanics in the 3 dimension, so you have to prove certain results that you used in the like 1 or 2 dimensional case to the 3 dimension case. Like you choose the, suppose that the Ehrenfest theorem. So we have discussed the Ehrenfest theorem, so now you can just use the 3D dimension analogy to prove the Ehrenfest theorem in the 3 dimension, and I guess that's also a question in the chapter number 4 of the Griffiths. You can check that, and this is also your kind of homework that you should do. These are quite easy. Okay, Ehrenfest theorem is quite lengthy. I mean, yes, it's lengthy even though we not discussed in the 3 dimensions. So in 3 dimension it will be quite lengthy, but you have to evaluate this. In 1 dimension it's like of 1 pages, in general cases it's like of 1 pages, but in general 3 dimension I don't know, because I have evaluated it, and using some sort of tricks I have evaluated in less than 1 pages. But if you will do all on your own with all of this mathematical stuffs, all of these rules, you will get it quite lengthy. I will share my another approach for proving the Ehrenfest theorem in 3 dimension, but at now you have to do on your own and figure it out, the 3 dimensions analogy of the Ehrenfest theorem. So this is the today's video. So thank you.